Okay, so in the previous lecture, we had started discussing about finite dimensional non-linear spaces. We have done two important properties. Please go and watch those two properties. The first statement we are going to discuss in this lecture is that let X be a finite dimensional non-linear space. Let X be a finite dimensional non-linear space. Then a subset of X, then a subset of X is compact if and only if it's closed and bounded. If and only if it is closed and bounded. Clear? Okay, so the proof of it. Now I guess we all know what compactness is. So if I just quickly recall, so in general, a subset being compact means that every open cover of that subset has a finite, subcollection. That is that is a subset is compact if it has a finite subcover. Then we have multiple definitions, like we have something called a sequential a concept of a sequential compactness, that every sequence has a convergent subsequence. Then we have something called the Fréchet compactness or the Bolzano-Weierstrass compactness, which is basically every infinite set has a limit point. And we have then something called a countably compactness, that is every countable open cover has a finite subcover. So, and all these definitions of compactness are equivalent in case of a metric space. These definitions are not equivalent. By definitions, I mean these compactness are basically different, different compactnesses, like the open cover compactness, the sequential compactness, the limit point compactness, so that is the Bolzano compactness, Fréchet compactness, and the countably compactness. These are typically four different types of compactness. But over a metric space, all four are equivalent. That is, if some set is compact, then it's also sequentially compact. It's also satisfies the Fréchet compactness, and it's also countably compact. Okay. So we are working in non-linear spaces. We know every non-linear space is a metric space. So under a non-linear space as well, every compactness is equivalent. So we can consider to justify whether a set is compact or not. We can consider any of the four compactnesses which we just discussed, and we will obviously use them accordingly. Now, one thing is one of these uh, you know implications is general. That is, if you have a closed and bounded set in a non-linear space, then it's compact. The converse is what specific for a finite dimensional non-linear space. So, um, just let A be in X. A be a set in X, and let A be compact. Okay. We have to show that A is closed and bounded. This again, which I was saying, is that this property is not specific or is not. It's not specific about finite dimensional non-linear spaces only. It's a general case that if you have a compact set, then it's closed and bounded. So let A be compact. We need to show that it's closed and bounded. So what we do is that we choose an element from the closure of A. Let us choose an element from the closure of A. So by definition of an element in the closure, there exists a sequence in A which converges to X. Therefore, there exists a sequence Xn in A such that Xn converges to X. Okay, one second. Yeah, yeah. So we have a sequence Xn in A such that it converges to X. Okay. Now A is compact, right? So if A is compact, then A is equivalently sequential compact. So there is a sequence Xn in A such that Xn converges to A. We cannot say that whether it converges in A or not, right? Now we have to show that typically that this convergence happens inside A. That is, this element X is in A. That is what we actually need to show, right? So we have a sequence Xn which converges to a point X, which we do not know whether it is in A or not. That is, we do not know whether the sequence converges inside A or not. But one thing we know is that since A is compact and Xn is a sequence in A, so Xn has a convergent subsequence in A. Right? So since A is compact, Xn has a convergent subsequence. But we know about the concept of uniqueness in the limit point of a sequence in Hausdorff spaces. Every sequence converges to a unique limit, and this property holds in Hausdorff spaces. We know a non-linear space is a topological vector space, so it's a Hausdorff space. So Xn has a convergent subsequence, and that subsequence must converge to a limit, which should be unique. But since Xn already converges to X, the subsequence must also converge to X only, because the limit point of the sequence must be unique, right? As a convergent subsequence in A, converging to X. But that obviously means that X must be in A, right? And so that means A is closed. Now you can obviously observe that we haven't used the concept of finite, X being finite dimensional in any. One thing which we have not discussed yet is what happens if A is not bounded. So we need to show that the boundedness of A is there. Right? So suppose A is not bounded. Okay, what happens if A is not bounded? If A is not bounded, then there exists a sequence Yn in A such that if I choose a fixed element B from A, then the distance of Yn from B is, it's greater than some positive number M. That is the definition for something being not bounded. So then there exists Yn in A such that the distance of each element Yn from B is greater than M, where B is fixed, where B belongs to A is fixed, and M is greater than 0. This happens obviously for all M. But what does this imply? This implies this sequence Yn cannot have a convergent subsequence. Right? Because its distance from B is constantly increasing. It cannot have a convergent subsequence, because if it is a convergent subsequence, the elements of the subsequence must come, they must come closer as you increase the value of the second index, but that cannot happen. Right? But if Yn cannot have a convergent subsequence, so it contradicts the compactness of it. It contradicts the compactness of it. Because we know since A is compact and Yn is a sequence from A, it must have a convergent subsequence. This contradicts the compactness of A. Right? Therefore, A must be compact, and so if A is compact, A is closed as well as bounded. But what about the converse? So what I just said is obviously the converse is not true in general, but it's true for finite dimensional spaces. Let's see. So now let X be a finite dimensional non-linear space, and let A be a subset of X such that A is closed and bound. Now we use the sequential criteria for compactness in order to check whether A is compact or not. For sequential criteria, we obviously need a sequence in A, so we do the what's necessary. Let Xn be a sequence in A. Let Xn be a sequence in A, and let us use a basis for X. Let E1 till En be a basis for X. Okay, simply because X is finite dimension. Then for each of these elements Xm, since A is a subset of X, therefore Xm is also an element of X. Therefore, each of these xm is a linear combination of these basis elements. Therefore, for all m, or I can simply say for all xm, there exists scalars. So for each I, we have scalars alpha I. So let's talk about say alpha 1m, alpha 2m, because these scalars should also depend on the index m, right? So alpha n m, such that this xm is a linear combination of these elements. So it's alpha I m of ei, I ranging from 1 to 2, right? I guess it's clear. Now A is bounded, right? Now A is bounded. So that means each of these elements xm, their norms are bounded. That is the specific meaning of A being bounded. That implies norm of xm is less than equals to some k. This happens for all m, and where k is some positive. Okay. But norm of xm is typically, you can use triangle inequality in this case, or you can simply write as norm of xm is nothing but norm of summation I is equals to 1 to n alpha I m. So this is less than equal to, right? But now we are to use lemma 1 of the previous lecture. So that's why I said the previous lecture is important. So from lemma 1, so there exists a positive number c such that norm of summation I is equals to 1 to n alpha I m ei. This must be greater than equal to c times summation I is equals to 1 to n mod of these inputs, right? These scales. Therefore, so suppose this is star. So what does star imply? So obviously this is, so if this is less than k, so this must also be less than k. So this implies summation I is equals to 1 to n mod of alpha I n m, right? Yeah, m is less than equal to k by c. Okay. But since each of these elements are positive, so each of these elements are positive, so this typically means for some fixed I, alpha I m, the mod of alpha I m is also less than equal to k by c, or rather, if even if we do not directly talk about k by c, for some fixed m, for some fixed I, alpha I m is also a bounded sequence, right? Is a bounded sequence. This simply because we are summing over non-negative numbers. So if the sum of a finite number of non-negative numbers is less than equal to some constant, so each of those non-negative numbers should also be less than equal to that constant, right? So alpha I m is a bounded sequence, right? But it is a bounded sequence of scalars. It's a bounded sequence of scalars. We know the bounded sequence inside the scalars because we have already chosen the scalar to be the real field or the complex field. So bounded sequence of scalars has a convergent subsequence because you can think them to be the bounded sequence. What are the scalars are? So they are basically real fields or the complex fields. What happens inside a real field and a complex? So this is very elementary analysis. These statements are very elementary analysis course that inside a reals, if a bounded sequence, then it's a convergent subsequence. Same holds for the complex field under the Euclidean norm if you think of it very specifically. So the bounded sequence, this implies bounded sequence of scalars, but this implies alpha I m as a convergent subsequence. We have already used the concept of boundedness. We have not yet used the concept of closedness. So there's a convergent subsequence, right? But suppose this, no, the subsequence of alpha I m, each of these alpha I m's are dependent upon xm. So if I consider a subsequence of alpha I m, take the linear combination with respect to the basis vectors, we get a subsequence of xm, right? In accordance with the subsequence, the convergent subsequence of alpha I m, we get a convergent subsequence of Xn. And since A is closed, the convergence happens in A. Happens in. So we started with the sequence Xn, and we show that there exists a convergent subsequence of Xn, convergent subsequence which is convergent inside A. So A is compact by sequential criteria. Right? So this implies A is compact. Right? Okay. Let us talk about the next important categorization. Now this is a fine categorization. This says that a norm-linear space V is finite dimensional if and only if the closed unit ball uh, generated or existing because of this non-linear space is compact. So I guess it's the fourth statement we are studying. A non-linear space V is finite dimensional if and only if the closed unit ball, as a closed unit ball constructed B, it has elements from V, that is vectors from V, such that the norm of X is less than or equal to 1. And this set is compact. Okay. So let's check the proof of it. Now notice one thing. Suppose V is finite dimension. Let V be finite dimension. Let V be finite dimensional. What can we say about the compactness of V? Okay. Now B is already closed. Right? B is already closed. Isn't B bounded? Let V be a finite dimension non-linear space. Right? Isn't B bounded? Every element of B has norm less than or equal to 1. Right? So B is both bounded and closed. No, closed. It's closed. That is given. B is closed and bound. Right? Because for all X in B, there exists M greater than 1, such that norm of X is this time. So B is closed and bound. V is the finite dimensional non-linear space. So what was the previous thing we just did? We showed that if you have a closed and bounded set of a finite dimensional non-linear space, it's compact. Right? So B is closed and B is bounded. V is a finite dimensional non-linear space, so this implies B is compact. Right? We're concerned about the converse of this. Let B be compact. B is clearly a subset of V, right? So let B be compact, and we have to show that V is finite dimension. Okay. Now, if B is compact, then it has a finite it has a finite open cover. Okay. So since B is compact, there exists a positive integer n. There exists a positive integer n such that, or I should say a positive integer n and vectors xi in B such that B is contained in the union of the open balls xi with radius center at xi, radius 1 by. Okay. We choose W to be the span of these xi's. Let W be the span of these xi's. So there are the finite number of xi's. Right. We have to show that W equals to. we claim W equals V. If W is equal to V, then V is a span of finite number of elements. It's easily finite dimension. Okay. So W equals to V. Suppose not. Suppose W not equals to V. Okay. We make use of the Rees lemma here. Okay. We make use of the Rees lemma here. I've not yet used the statement of the Rees lemma, but let me give the statement of the Rees lemma. It will be then easy to use. Okay. So let me just write the statement of Rees lemma here. Rees lemma. Okay. Statement is as let V be a non-linear space and W be a proper closed subspace of V. And W be a proper closed subspace of V. Okay. Subspace, mind it. Then for all epsilon greater than 0, we can find a vector u epsilon such that norm of u epsilon is equal to 1, and that is each of these u epsilons are unit vectors, and the distance of u epsilon from the subspace W is greater than or equal to 1 minus epsilon. Clear? Clear? So we use this here. So we have, so suppose W is not equal to V, and clearly W is a subspace of V because it's a span of vectors from V. So W is a proper subspace of V. That's quite obvious from here. Right? And obviously W will be a closed set as well because it's a point set. It's clearly a point set. So therefore, we can apply the Rees lemma here. By Rees lemma, we have u epsilon in V such that the norm of u epsilon equals to 1 and distance of u epsilon from W is greater than or equal to 2 by 3. Okay. Now, since the norm of u epsilon is 1, therefore u epsilon must be an element of the closed ball. Since norm of u epsilon equals to 1, this implies u epsilon is an element from B. It's an element from the closed ball. Okay. And distance of u epsilon from W is greater than or equal to 2 by 3. Right? So this typically means norm of u epsilon minus xi is greater than or equal to 2 by 3. This happens for all I is equals to 1 to n because W is spanned by these vectors xi. Right? Right? Which is a contradiction. It's a contradiction because the distance of u epsilon and xi can never be greater than or equal to 2 by 3, as the set B is itself union of the open balls with center at xi and distance 1 by 2. Right? And u epsilon is an element from. So distance between distance between an element of B and at the center xi can never be greater than or equal to 2 by 3. I guess it's now clear. Right? So therefore we reach a contradiction and hence W must be equal to 2 because the contradiction arrives due to an assumption that W is not equal to 2. Right? Okay. Let's think about something more. Yeah, we can also talk about a continuous linear operator over a finite dimensional space. That is a linear operators defined over finite dimensional spaces are always bounded. And if we know that a linear operator over a non-linear space is continuous, then it's bounded as well, and if it's bounded, it's continuous. The continuity and boundedness are equivalent statements over non-linear spaces. So we can actually show that every linear operator defined over finite dimensional non-linear spaces are bounded, or rather are continuous. So I guess this statement 5. every linear operator over finite dimensional non-linear spaces are bounded. How do we prove this? So what is a linear operator over non-linear spaces? So it's basically a linear transformation, nothing else. It's simply a linear transformation where boundedness typically means, let me just clarify it. Suppose x and y are non-linear spaces. X and y are non-linear spaces. Then t from x to y is a linear operator if it's a linear transformation as xy being vector spaces. Okay, as xy being vector spaces. What is it? What do we mean by t being continuous? So we know that x and y are non-linear spaces. Hence, they are metric spaces. We know every metric space is a topological space. So if T is a mapping from X to Y, which are non-linear spaces, so we can think of T being a mapping between two topological spaces. And in between topological spaces, we can talk about continuous functions. Simply. So T from X to Y is simply a continuous function or a continuous linear operator. Firstly, if it's a linear operator. Secondly, if the inverse images of every open set from Y is an open set in X. That's all. Very simple. Or you can simply go by the delta epsilon definition of continuity as well, which holds in metric spaces. Whatever you feel like. What is it being bounded? So it's said to be bounded if the norm of Tx is less than equal to some positive value k times the norm of x for all x in capital X. In this case, we say the linear operator is bounded. So boundedness and continuity are equivalent over non-linear spaces. We have to show that every linear operator over finite dimensional spaces are bounded. How do we show this? So let x just put this up. So let x be a finite dimensional non-linear space, and um, let us choose a vector. Sorry, a basis. E1, E2 till En be a basis for x. Okay. Therefore, for all x in capital X, it's a linear combination of uh, these basis elements. So this is I equal to 1 to n, where each alpha I escapes. Right? Here. So if we have a representation of x, using this we can represent t. What is t of x? So it's t of summation of I is equals to 1 to n alpha I ei. So t is a linear transformation. So the summation comes out, the scalar multiple comes out. We are left with t of x. Right? What is the norm of t of x? The norm of t of x is the norm of summation I is equals to 1 to n alpha I t of ei. But then we can use the triangle inequality. So this is less than equals to summation I is equals to 1 to n t of alpha I, norm of alpha I times t of ei. But we can again bring alpha I outside as a modulus of it. So mod of alpha I times norm of t of ei. We can choose the maximum of t of ei from here. Right. We can say this is less than equals to k times summation I is equals to 1 to n, mod of alpha I, where k is the maximum of the mod of t, norm of t. Okay, hydrogen from 1. But again but we know that c times there exists a positive number c such that c times summation I is equals to 1 to n mod of alpha I. This is less than equals to summation I is equals to 1 to n, norm of this alpha I ei, where ei is a linearly independent set as we have. Right? This is from lemma 1. Lemma 1. What is summation I equals to 1 to n alpha ei? So this is nothing but norm of x. Right? So this implies summation I is equals to 1 to n mod of alpha I. This is less than equals to 1 by c times norm of x. But we have k times summation equal to 1 to n of mod of alpha I, so we can consider k here. We multiply k here. Okay. But this implies that norm of t of x is less than equals to, we have k by c norm of x. Obviously c is positive, k is positive, k by c is positive. So we have this, right? So this abides by the definition of norm linear of a bounded linear operator. So this means t is a bounded linear operator. Hence, also a continuous linear operator. Okay. So typically, every linear operator defined between finite dimensional normed linear spaces are uh, bounded, hence continuous. Okay. I guess it's clear. Okay. Uh, okay. So meet you guys in the next lecture. In the next lecture, I'll try to. Yeah, we have one more thing. We won't discuss it here. As I was saying in the previous lecture, one more important categorization is left. Then we will talk about Banach spaces independently. What are the examples of Banach spaces and what are some important properties of Banach spaces. Next lecture we start with the property that a norm linear space, if a norm linear space is locally compact, then it is finite dimension. Local compact means if you choose an element x, I mean for every element small x, there is an open neighborhood of it, whose closure is compact. Okay. Whatever. Meet you guys in the next lecture.